Hello everyone, let's come back to GCSE and iGCSE, the topic sets. Before I explain sets and Venn diagram, make sure you watch that. If not, please first watch the explanation because they're crucial things were explained and only then come back to revision. So in the revision, you can see several examples. This is example 1. You can consider them as a problem for you guys for self-practicing, and only after you accomplish them by your own, so please try to see explanation. So never see explanation, never watch explanation before you actually try to do by your own. So grab your pens, grab your notes, pause the video, try to do by your own, and only then compares. All right. So, and we start from the first example, the first problem. It's all about set basics. So, you have set U, which is universe. It's represented by consecutive positive integers from 1 to 15. So, what does mean consecutive? Keywords here, and in many problems you can actually hear these words. All right, so consecutive means they goes each after the other, and this term refers to actually integers. So that's why you only need to apply to integers. They cannot be like consecutive real numbers. Alright, so if there are positive, find numbers of elements in each set. So that's why first of all I just list elements of the universe. That's why I start from 1, 2, 3. I just miss them and skip, and the last element is going to be 15. All right, so sorry for my curly brackets, sometimes not really useful to write by electronic pen. All right, so we've got that, and that means number of elements. You remember this notation for sets, and from U is going to be 15. You just need to count them. All right, so what about set S? 1, 2, 3, 4, 5. So number of S in set S is going to be 5. All right, and number of T is going to be just 2 elements. All right, so S and T are actually subsets in set U. If you just put this onto Venn diagram, you can see a rectangle representing universe. Actually, there will be 2 circles, S and T. So probably they will have 2 elements in common, 7 and 10. So that means that actually T is going to be inside S. Okay, so you can write even T from S because T is the proper subset which contains part of the elements S, and they're not equal. All right, so using Venn diagram, if you like to illustrate and maybe just understand more visually, if you're more about visual understanding, so it's highly recommended to put those sets as circles on the Venn diagram. All right, so we need to list not S and not T. Okay, so in this case, not S is everything except for S within universe. So that means we just can list elements for S except for which contained in set S. So that's why we start from very beginning, 1, 2, then 5, then 6, 8, 11, 12, 13, 14, 15. Okay, so I'm not going to list all elements for not T, but you understand that it's going to be any element X, so that X is not from T, so you can crisscross that, so cross it out, but X from universe, of course, so X should be adhered to universe. Alright, so and, you can write and. So, but you can also list because the question is about listing, so you need to list. Okay, so in C part, which is incorrect. So S is the set from U. Is it correct? Of course, yes. So it's might be proper, it might be improper subset. So this equality means that S might be equal to universe. But actually, it's if this is true, so in general case it's true, So you need to write that's true. That's true. Okay, so what about T? From here, it's also true because T contains every single element. Universe contains, of course, 7 and 10, so that's why it's definitely T from U. Okay, so next one. S from T. It's obviously false. False, because if you put elements T, you will have only 2 elements. While in S, yes, you do have 7 and 10. However, S set is much bigger because on top of that it contains 3, 4, 9 as well. Okay, so that means it contains more elements than T has. So that's why that's definitely false. And T from S, it's true because you can find every single element from T in S. So that's why T from S. So if you put in a circle, so you can write definitely, or you can draw a circle in this way. So it's going to be circle S, and inside there, that's going to be circle T, containing 2 elements. All right. So I hope you understand. I hope it's clear for you guys. So S and T. And we go next. So if set M, represented by elements 4, 10, 7, 11, 9, and A, some unknown element A, and you also know that both M from universe, and you also know that S from M, okay? That's key here. So set S, that contains elements 3, 4, 7, 9, 10, is from M. You need to find element A. All right, so how to do that? I think it's better to draw a part of Venn diagram. You don't need to put the complete Venn diagram. It's enough to depict 2 circles. So obviously set M contains elements 4, 10, 7, 11, 9. It contains a bit more than S. However, it contains specific element A, and set S contains element 3, which M doesn't have. So what we can do? We can do the following. So we can depict set M here and set S somewhere here. Not like this, it's like that. All right, now what I'm gonna do, I'm just going to put elements in the set S first. Okay, so this is set S. Which color to use? Okay, this one is better. So this is set S in interior circle, and let's put elements. So 3, 4, 7, 9, and 10. Why I know that circle S and set S within the set M? Because we know that S is a subset of M. So that's why M should contain every single element from S. Okay? So because we have for M elements like 11 and yes, and element A, so we definitely can say that 11 stay somewhere a part of S. So it doesn't adhere to S. So but it contains so M said M contains this element. However, what about A? Because we know that so a set M should also contain 3, okay? And we have element A. A cannot be any number except for 3. Because, okay, assume that A is 12. In this case, we put this A element here. However, what about 3? M doesn't have, in this case, element 3, but it should have because S contains that, and we know that S is subset. So obviously, A is not 12, but 3. So that's why element A is here. Okay, it both contains an M and S, that's why it's 3. Okay, so A is 3. So the last one is any from sets U, S, M, T, infinite. So what about, what does mean infinite set? I just remind you, it's not limited, okay? It should contain infinite number of elements. For example, let's consider set z plus, z minus, or just z positive integers, okay, for our case. Obviously, it's infinite because it's restricted from top, from the bottom, from the lowest number, it's 1. However, it's not restricted from the top because elements goes to infinity. So in this case, because we can count elements and this is going to be specific number, not uncertainty, not infinite number of elements, so we can say that no single set is infinite. They're finite in contrast. Alright, so let's move next. Alright, so we are on example 2. So in A, you need to list all subsets of 1 and of 1 and 2. So you have sets and you need to actually list all possible combinations of elements. So because the first set contains only one single element, we will have only one possible combination because of the one element. And also, empty set is going to be a subset for any set. So that's why empty set is always is always a subset of any set. So that means you have, for set of one single element, you have two possible subsets. So I just fix the number 2 for set of one single element. And here are two elements. Alright, so let's list all possible subsets. Normally you need to start from empty set because it's a very good starting point, so that you won't forget it later on. Okay, so that's one subset. Next, let's consider subsets with one single element. So that's why just 1 and subset of 2, they're also subsets of the set containing 2 elements. Alright, now the last one is just combination 1 and 2. Alright, so why I'm not writing 2 and 1 as one possible subset? Because so actually it's subset which is equal to 1 and 2 because order in this case doesn't matter. Okay, so we consider combinations. So that's why no matter how you write in increasing order 1, 2 or in decreasing order 2, 1, so it represents the same subset. Okay, so in this case we have 4 possible subsets. Alright, let's get next. So you need to list all subsets for 1, 2, and 3. So in this case, you'll have 3 elements. Alright, so if you can predict, try to predict. If not, just try to work out because it's too early, I guess, to predict how many possible combinations of subsets you might have. Alright, so first of all, it's just empty set. Next one is just 1. Next, 2 subsets containing only one single element, 3. Now let's consider subsets containing 2 elements. So that might be 1 and 2. This might be 1 and 3. This might be 2 and 3. Okay, so and the last starting point, so we start from empty set, then single subsets with single elements with 2 elements, 1, 2, 3, 4, 5, 6, 7, and I guess there is one more, basically improper subsets, which becomes actually set itself. So that's why the last combination is going to be 1, 2, and 3. 1, 2, and 3. So in this case we have 8 possible subsets. And now we need to try to predict the number of subsets 1, 2, 3, 4 without listing them. Okay, so guys, of course, you can predict using just aggregation principle. So basically, it's all about how you recognize the patterns. Let's consider when we have, I just try to complete the table. So if we have a number, so let's say we have a table. So let's complete this table in this way. So here and also here, okay? I think it's going to be enough. So here we put number of elements, okay? And here is going to be number of subsets. Okay. When there is one single element in the set, we have two possible subsets, okay? When we have two elements, 1 and 2, for example, we should have 4 possible subsets. When we have 3 elements, we should have 8. So, like, guess what? There are actually, as you understand, the next number of subsets, so for example, for 4 elements, this might be the rule that every time you multiply by 2, so it's sort of geometric sequence, multiply by 2. In this case, you'll get 4 by 2 and 8 by 2. So that's why it's going to be 16. So every time you multiply by 2. In other words, for 4, so for the set with n equals 4 elements, you'll get all possible subsets combinations using the formula 2 to the power 4, which is 16 in this case. So previous case, that was 2 to the power 3 for the set of 3 elements. So that's why derive the formula using generalization technique for all possible subsets, as we established on the previous step. So we should have 2 to the power of n, okay? And hence otherwise predict number of all possible proper, so proper subsets. So proper except for the last set itself, so that's proper subsets. So that's why it's going to be 2 to the power 4, but you take away a subset that actually improper, 1, 4, 7, and 10. So you just take away, that's why 1 from here. And that's going to be how many to the power 4 minus 1 is going to be 15. So 15 proper subsets. So be careful because proper. And we can move on. So example 3. You need to list the elements of the set S, which actually S from Z plus, which contains the factors of 8. Alright, so what we can do, we just simply we need to list all factors of 8 and include into set of S. So it's going to be obviously 1, 2, 4, and 8. They are possible factors because Z plus they're positive, so that's why you cannot consider negative numbers. So next one, multiples of 6. So in this case, we need to put the following starting from 6. So multiple is a number that is divisible by your number which is given here. So that's why 6, and every time just add 6 every time. So it's going to be 12, the next is 18, then 24, and so on. Is it limited? Is it infinite or finite? Of course it's infinite because you can imagine like many multiples, and this number of multiples is going to be infinite. Alright, factors of 13. So again, every time you started from 13, adding every time 13 to the previous number, 39, and so on up to infinity. So both sets are infinite. So prime numbers less than 25. So in this case, you just need to list prime numbers. As you remember, prime numbers starts from 2. It's only even number in a row. Next, there will go only odd numbers, but not every. But so that prime number is a number that consists of itself and another factor is just 1. Okay, so you can represent prime number only as the product of 1 and itself, the number itself. So 3, 5, 7, 11, 13, 17, 19, and 23. That's going to be the last number because less than 25. So less, strictly less, that means it's less. And because z plus, we need to obviously list integers. So odd number less than 25. So in this case, your set is going to be more, contains more numbers. So odd numbers starting from 1, then 3, then 5, then 7, 9, so 11, and so on up to odd number up to 23, because 24 is less than 25, but it's not odd number. So 25 we don't include because it's strictly less. Okay, composite numbers between 6 and 20. All right, so composite numbers between 6 and 20, we consider this number as strictly more than 6 and strictly less than 20, so that's why we don't include boundary. Okay, so we can list easily. That's going to be starting from 8, then 9, then 10, 12, 14, then 15, 16, and I guess 18 is going to be the last one because strictly less than 20. Alright, so hope you got it. Hope you have the same solution to the problems. And finally need to prove that the following statements are true. So prove just the following statements. That is just redundant words. Sorry for that. So the sum of irrational numbers might be a rational number. Okay, so what does mean a rational number? Examples are square root of 2, square root of 3, square root of 5, for example, where it's not possible to evaluate square root. Actually, irrational number are numbers where you don't know the rule how the next digit is arranged. Okay, in this case, for example, if you use calculator, you can calculate square root of 2, but it will give you a result up to certain digits according to let's say precision of your calculator, how many digit cells it has. Okay, but for the next digit you have no idea what it's going to be. Okay, so that's why we need to prove that the sum of irrational numbers might be rational. Alright, so for example, if we take square root of 2 plus square root of 3, obviously the result is going to be irrational. But there might be some cases where it gives to you a rational number as the result. So you just simply need to pick up, one example where you have rational number as a result. So this is still irrational. You just prove that sometimes it might be irrational, sometimes it might be irrational. So how to prove that finally you can get rational? Just because you're not restricted in terms of what types of rational number you can take. For example, you can take the same numbers and you can take also negatives, because there is no any single word about should be positive or negative number. So that's why I'll take square root of 2 or let's say square root of 5, and plus I add negative irrational number, which is negative square root of 5. As the result, you will get 0 because they will cancel each other. Alright, so that's why you prove that. So the last one, the product of irrational numbers might be rational number. Alright, which example to take? So if you take, for example, square root of 2 times square root of 3, you'll get square root of 6, which is also irrational. However, if it takes, so that's irrational result. However, if you take the same numbers, like square root of 2 times itself, you'll get square root of 4, which is a whole number, 2, or integer. So that's why you can easily prove. Again, so if you need to prove something like some just minor cases, like in this case, just try to think about possible numbers that satisfy your conditions. All right. If you're gonna prove, for example, more general statement that which is actually true, you also which is false. So you have the statement and you need to prove that it's false in some cases. You just need to pick up one example, and one example where you have contradiction is enough in order to prove. All right, or you can prove in general way, like using mathematical induction and mathematical induction principles. However, this is more about A-level stuff or IB. So here in GCSE, it's less likely you will have you'll have to prove using mathematical induction. Alright, so hope you like that. There was I think good revision. We revised sets, so sets basics. Next time I think we'll revise Venn diagrams. Sorry again for sometimes I disappear from the channel and I don't create some video because I'm traveling across Russia. This the whole trip, the whole story. It's all about like traveling, and it's all about dancing because I used to film different so my dance style in different places, different spots, and so that's why sorry for that. Sometimes you might miss me. Okay, so if you don't want to miss me, so please subscribe to my dance channel. You'll find lots of clips for the time it exists. All right, and hopefully I'll arrange also a new channel dedicated to travel vlog. If you like traveling, I think it's gonna be useful for you guys. Hope you like that in general. Don't forget to subscribe if you're new here, share, likes, you know what I mean. Thank you, and see you next time.